Hey everyone, and welcome back to Star Studies. This second episode is all about astronomical detection of light. And before I begin, I do want to clarify that almost everything I'm presenting here in these first few episodes are the results from many other physicists and astronomers whose discoveries I'm applying in my research. So I don't deserve the credit for almost everything that I'm presenting here at first. I will start explaining my own findings once you have the background necessary to understand it, but at least for this start, it's all previous studies that other people have done. So, astronomical detection of light. Why is this important? Well, it's important because in reality, the only way we can study things in space that are so far away from us is by observing the light that they either give off or reflect. And that's really all we have access to in astronomy. And fortunately, as human beings, we're very used to working with light. If you're out in the middle of the night on a road, you'll see lights all over the place, meaning different things and used for various functions and stuff like that. But we're very familiar with working with light, and we need it all the time. And that's exactly the same case in astronomy. We need to use the light given off by other objects in space. I guess the only exception to that would be the use of gravitational waves. But at least with the instrumentation that we have so far, those really aren't useful in studying stars. Really, they're only useful in studying supermassive black holes so far. So, overall, if we want to research stars and learn more about them, we need to use the light that they give off. So, let's start by talking about the basic physics of light. As you are probably very well aware of, light is a wave. And what a wave in general is energy traveling through space with this wave crest, wave trough pattern that I'm indicating here in this image. And because light is a wave, just like any other type of a wave, it has a characteristic called a wavelength, which is indicated here in this image as the distance between one crest and the next crest. And it's actually the wavelength of light that determines the color of light. And as I'm indicating here in this image, as we know, we can see any color from dark red to really dark violet. And violet, or blue, or purple, or any of these colors that are similar to those are the ones with the shortest wavelength, somewhere around 4,000 angstroms. That's what that A with the circle at the top means, or in other words, 400 nanometers. That's about the wavelength of the most purple or violet type of a color that humans can see. And red, which is somewhere between 6,000 and 7,000 angstroms near the bottom of this image, is about the most red that the human eye can see. And it's got the largest wavelength out of all the colors we can see. And so wavelength corresponds to color, and the shorter wavelengths are violet, the longer wavelengths are more red. But there's actually a lot of light that we can't see directly with our own eyes. And in this image that I'm showing you now, this is what's called the electromagnetic spectrum, where at the top there's this wide range of wavelengths with the larger wavelengths on the left here and decreasing towards the much smaller wavelengths on the right. And along with that, they're indicating the different types of waves that correspond to those wavelengths, with the visible light indicated here at the bottom with this rainbow type thing being such a small amount of all the wavelengths light could take on. For wavelengths that are larger than about 700 nanometers, which is the wavelength of red light, the light is no longer visible, but is actually called infrared light. And if we go to even larger wavelengths, the light becomes radio waves, which is basically the type of light, if you want to think about it that way, that we use for Wi-Fi, our cell phones, and most communication devices these days. And then on the other side, light that has a wavelength smaller than about 400 nanometers is called ultraviolet light. And then if you go to even shorter wavelengths than that, it turns into what's known as X-rays and gamma rays. So in my research, I used the infrared light given off by stars. So it's light that you can't see with the human eye, but you can still learn a lot of science from it. And I'll explain why we used infrared light in a minute. So that's one fundamental about light, its wavelength. Another characteristic of light, again because light is a wave, is its amplitude. How high are the crests and troughs is basically what amplitude is. And it's not completely correct, but it's not bad to think of amplitude as a measure of how bright the light is. So with these two characteristics of light, wavelength and amplitude, we can ask the question, if we look at a star, what is the amplitude of its light at a particular wavelength? A simpler way to ask that question is, how bright is the red light, or the blue light, or the green light, or any other wavelength of light given off by a star? How bright is that light? And this is the technique that is called spectroscopy, which is what I used in my research. So in a nutshell, spectroscopy is studying the light from an object, it can be any object, once that light has been spread out over a range of wavelengths. That's really all spectroscopy is. But when we look at stars with our own eye, or with a telescope actually, such as those shown in this image right here of M67, the light coming from that star is all clumped together into, well, basically a point. So it's not spread out over a wide range of wavelengths. So how do we get it to spread out? Well, we need to use something called a diffraction grating. And in here in this image, this is an illustration of basically what a diffraction grating does. And really all a diffraction grating is a large collection of very small slits that the light passes through. And there's a whole realm of physics called optics that's behind this, but basically when light passes through a whole collection of small slits like this, it works very similar to sending light into a prism, which you're familiar with. If you do that, it sends the light out in kind of like a rainbow pattern, which physically that is spreading it out over various wavelengths. And I actually wanted to demonstrate this here with a really good pair of diffraction grating glasses that I have, but the human eye is really the only way you can see it, so it wasn't able to be caught on camera. But I highly recommend going and buying your own pair of diffraction grating glasses. And they're actually pretty cheap these days, only about $5 or so. And once light has been spread out over a wide range of wavelengths, we call that a spectrum. Now, the organization that we got all of our data from is called Apogee, and that stands for Apposh Point Observatory Galactic Evolution Experiment. And what Apogee did is they used a $1 million version of a diffraction grating to collect light from individual stars all over the Milky Way galaxy. And as I mentioned in the previous episode, because stars in open clusters, such as M67, are much more spread out over space than the stars in globular clusters are, it's actually easier to observe individual stars one at a time in open clusters. And interestingly enough, Apogee decided to look at the infrared light from stars rather than the visible light. And why is that? Well, it turns out that with all of the dust that's in our galaxy, that can easily block a lot of the light. Infrared light, unlike visible light, actually is able to make it through most of that dust without getting blocked, simply because it's got larger wavelengths. So we got infrared spectra from apogee, and now I'm basically going to show you what one of these spectrum looks like. And let's start with the visible spectrum from the sun. Now, since the stars that we study in M67 are very similar to the sun, this spectrum that you're seeing right now would look very similar to what the visible spectrum of the stars that we studied in M67 would look like as well. So what you're seeing here, again, you'll see this rainbow pattern again, but you'll also notice that there are some very narrow dark lines here. Some of them are darker than others, and some of them are even more narrow than the others. And I'll be explaining what those dark lines are and how we use them in a future episode. And we used them a lot. Now, if we look at the infrared spectrum of the sun now, we can see that it looks quite similar. There are still these dark lines here, and there are various colors, except it's important to be aware of now that these colors are fake, because at least to the human eye, infrared light has no color. I just created this image with a Python program that I helped to write, and I colored it based on the different wavelengths that the light has. Now, if we take this infrared spectrum of the sun and turn it on its side, we can make a graph of how bright the light is, which is shown on the vertical y-axis here, for various wavelengths, shown on the horizontal x-axis here. And this might look actually quite a bit messy, but believe it or not, there is so much information hidden in this spectrum. And if we zoom in on a particular area, it looks something like this. And you'll notice that we have these very narrow dips here, which are basically the same thing as those dark lines we were seeing before. And basically all of the results that I got in my research came from spending literally hundreds of hours sitting at a computer analyzing spectra like this for stars in M67. That's how valuable a spectrum like this can be. So, I hope you've learned a lot about how we detect light in astronomy from this episode, and particularly what the spectrum of a star is. In the upcoming episodes, I'll be going deeper into how we learn certain things about a star based on its spectrum. So, may the Force be with you, and I will see you next time on Star Studies.